Hi, I'm Joel Kira, assistant professor at Georgia Tech. I'm sorry I won't be able to give this talk in person, but I hope everybody is healthy and well. And I'd like to thank the organizers for inviting me. Today I'm going to be talking about improving label efficiency through complex data augmentation and a few things beyond that. So there's been a lot of tremendous progress, very fast-paced progress in dealing with machine learning settings where you have reduced number of labels. So this includes zero few-shot learning, semi-supervised and self-supervised learning, domain adaptation, and so on. And really, these methods have leveraged a handful of very simple methods. So for example, data augmentation, which we've known about a lot, but has become kind of very critical in some of the latest methods, such as FeatMatch and CLR and so on. Pseudo-labeling and distillation similarly have been important. Surrogate tasks have been developed for self-supervised learning. And then there's some more sophisticated kind of methods leveraging prototypes or clustering, as well as graph neural networks. So here in bold, we kind of show some of the methods that we've been kind of pushing forward on. And so my lab has made contributions across these different settings. So we've made some early contributions in looking at how to leverage pairwise similarity learning or metric learning to do cross-task object discovery. So here we have a labeled data set with one set of categories and an unlabeled data set with another set of categories. And the idea is we need to cluster the unlabeled data and figure out what to transfer from the labeled data. So we have some optimization loss functions that we derived for this problem. We've looked at few-shot learning with Virginia Tech. We've developed methods for complex data augmentation for domain generalization and semi-supervised learning. And then we have some more recent work on video domain adaptation as well. And so for this talk, I'll really be focusing on the complex data augmentation idea, but you can look at some of the papers to see the other work as well. So in terms of data augmentation, obviously it's been a key kind of method. We've known about it for a while, but has really been pushed on for several machine learning settings, semi-supervised, self-supervised learning, and so on. And there's been methods developed such as randomized domain or data augmentation, where we have a list of, let's say, 100 different augmentations, for example, from an image processing library that performs various forms of transformations. And of course, this requires some domain knowledge, right? So computer vision experts know what types of transformations we'll either have in the testing set and that won't destroy semantic information in the image. And so what we've been looking at is how can we reduce this domain knowledge and specifically have methods that can work across various domains and modalities. And what we want to do is be able to automatically, for example, learn different types of data augmentations by leveraging deep learning, various features of deep neural networks. So the first method that I'll talk about is in the setting of domain generalization. So you may know about domain adaptation, where you have a labeled source set, and you're trying to generalize to a target set that has unlabeled data. So you're given this unlabeled data a priori, and you can develop various methods such as aligning the feature distribution. Since feature extraction doesn't require labels, it just requires the data. We can try to align the features between the source and target and do better domain adaptation. So there's a ton of different works in this setting. What we're looking at, on the other hand, is a little bit harder, which is domain generalization. So here you don't have any information about the unknown, about the target. You're not even given unlabeled data, and you also don't know what it will be. And so we know that neural networks generalize well when test data is in domain. And because we don't know anything about the target, this is actually a scientifically interesting problem because we really have to choose the proper biases to enable generalization for out-of-domain data. So one example is we might have to ignore good features that work well for the training. So if you're just using empirical risk minimization, you might think that textural features, for example, are very generalizable. But once you have images from infrared or sketches, things like that, it's no longer going to be effective. And so there's been actually a lot of really interesting work looking at biases within CNNs. specifically shape versus texture. And so, there's been a lot of work showing that these biases actually are much heavier in humans, but actually CNNs tend much more towards texture, for example. Here's an example of kind of texture and domain shift. So if you have dog images across all these different modalities, then you really can't rely solely on texture. And texture might actually produce some noise in terms of if you want to train on these images, the real world images, and generalize to sketches, for example. So what we specifically want to develop are methods that, or training procedures that enable the model to ignore such irrelevant information. And so the key to doing this is, we think, leveraging implicit variability within the source domain. So in domain generalization, you're not just given one source domain. You have, let's say, 4 of them or 3 of them. And what we want to say is that we have these 3 domains during training. Can we understand what kind of variability exists within these data sets and across these data sets to then impose in our neural network model some sort of invariance to these irrelevant features. So we want to leverage cross-source data and through data augmentation, make our models more invariant to the features that are not generalizable across these different sources. And so, again, our goal is to train one model that focuses on more of these generalizable features such as shape and ignore irrelevant features such as texture. So sort of a simple approach that we've developed actually does this through stylization. So the question is, how can we leverage the implicit information, biases and irrelevant features that exist or variability that exists within our source data sets to make our models more robust? And so our question was, can we just use stylization to do this? So for those that don't know about stylization, really the idea of stylization is that we have a content image, so an image that we want to preserve content for, and then we have a style image. So for example, different painting styles and so on. And so what we're going to do is automatically generate an image that preserves the content while also maintaining the style. And so typically the way this is done is there are several different losses. There's a content loss that makes sure that across various different layers in our neural network that extract features, the content of those features is preserved across the image that we generate and the original image. And then we have another loss that maintains style. And the way that's often represented is something called the Gram matrix, which is just the correlations between, pairwise correlations between feature maps within our neural network. And again, you can choose which layers to apply this to. And so you're going to optimize an image, so actually create a new image that has these losses associated with them. And then you can do this explicitly by, again, applying the style loss with respect to the Gram matrix, but this is actually pretty slow. So there's newer methods called add-in, for example, that do this much faster. And so what we're going to do is we're going to, for example, look at different domain generalization data sets, such as PACS, which has photos, art, cartoons, and sketches. What we're going to do is we're going to actually take 3 domains that are selected as the source or training domains, and then we'll have an last domain essentially be the test domain, and we're going to cross-validate. So we're going to pick many pairs or triplets of 3 source domains and pick the last as test. And so what we're going to do is we're going to test stylization as an augmentation method. Specifically, we're going to take the training set sources and essentially augment them through stylization. We're going to stylize them as painter by the numbers, which is an external data set. So the style loss will be driven by these painting styles. But we actually also look at within source. So the question is, if we just stylize one source domain to another source domain, we're not using an extra piece of data, such as painters by numbers, but can we actually still, pick out these implicit biases or irrelevant features or variability that exists within the source domain? And so There's a lot of actually related work and current methods for domain generalization. I'm not going to go through them, but suffice it to say that they're pretty complex. So they involve things like meta learning and so on. And so what we are actually looking at is a very simple method. We're just going to use stylization as data augmentation and just do normal training after that. We're not going to use any of these more sophisticated methods. So looking at the PAX dataset, when we stylize using the style of paintings, various paintings, we actually get state-of-the-art domain generalization results. And so, again, through a very simple method, just add domain data augmentation through stylization. And again, here we're using the painters by the numbers as the source of stylization. Obviously, the downside is here, it's not quite fair comparison because we're using an extra data set as a source of information. And so what we've asked is, can we actually stylize within the sources themselves? So again, the sources themselves provide some biases or variability. And so here, for example, we show some examples: artist cartoons, artist photos, and artist sketches. And we're just going to take pairwise, sources and stylize them in this manner. And what we show in the results is actually, this is actually quite competitive with using the external source. And in some cases, actually a little bit better, you'll see in other data sets. So we can actually, without using extra information, we're just literally using the 3 sources of data that we have, and we do either intra-source stylization, which actually literally does not stylize across the different domains, it stylizes just within one domain. So it turns out there's enough variability within one domain even to do pretty well. And then we can even get a bigger boost by actually stylizing across the domains themselves. So this is really interesting and maybe unexpected because we initially did not think this would work if we didn't use an external source. We've actually done this rigorously across many other data sets and find the same kind of state-of-the-art results. And again, even intra-source or inter-source does really well in these cases. So there's a question of kind of how can we understand what this method is doing? And so we can leverage a lot of these cool related work that have looked at shape versus texture bias. So obviously, one of the key forms of variability that we can understand in these data sets is texture. And so what we can do is actually try to ascertain, does our form of data augmentation through stylization affect this texture shape bias? And specifically, the way we do this is a little bit cumbersome, but what we do is we take, for example, sketches, where you see sketches of different objects, such as a dog in this example, and then we actually pull apart textures from online and essentially, for example, giraffes, and actually create a Q conflict image where we have the shape of one thing, so the shape of a dog, and the texture of another thing, in this case, the texture of a giraffe. And we can actually measure quantitatively 3 different things. We can measure the bias level. So I won't go into how you measure this, but it's a quantitative number, again, pulled from related work, which essentially tells me if I have this Q conflict image, how does my model predict this image? Does it actually tend towards the shape of the image, or does it tend towards the texture of the image? We can also learn additional neural network linear layers that actually directly predict from this Q conflict image the shape and the texture of the image. So can it predict that it's the shape of a dog and the texture of a giraffe? And so this is a little bit measuring kind of predictive accuracy rather than just bias. And so what's interesting is that this is showing the shape and texture accuracy. What we show is that when we do our stylization, we actually don't affect much the texture accuracy. So it's interesting. The features still have texture information in them. It's just that the classifier part actually is biased towards listening more to the shape. But we do increase shape accuracy, meaning that the features that we're learning we're learning more kind of shape-based features as well. So kind of interesting results there. And what we show is that in terms of shape bias itself, the more complex you get in terms of augmentations, including when we add our stylization-based data augmentation, we significantly increase the shape bias. So we can kind of understand that increasing shape bias is actually improving domain generalization. As we can see, it's kind of correlated with domain generalization results, and our domain adaptation or data augmentation, methods does actually increase this shape bias. So there's a lot of future work that we can do here. So obviously stylization is one kind of method that maybe picks out more textural kind of variability, but there might be other variability within the sources themselves that we can try to pick up automatically. Again, the key idea is to kind of remove the need for performing data augmentation in a way that requires a lot of domain knowledge, where we have to list 100 different types of data augmentation. So next I'm going to talk about another line of work that we've done, again relating to data augmentation, but in this case using graph neural networks. And specifically what we're looking at is the question of, can we leverage the structure of the manifold itself through graph neural networks to perform complex data augmentation. And so the setting here is semi-supervised learning, where you have a small amount of labeled data and a large amount of unlabeled data. The example data sets are very typical: SVHN, SciFar, Mini ImageNet, and so on. And the previous kind of state of the art here leverages data augmentation, specifically just simple augmentations such as flipping and rotation, things like that. Or in some cases, what's called mix-up, where you interpolate between images and also interpolate between labels. And so the idea for mix-match is essentially to perform these data augmentations on the unlabeled data and enforce that the predictions on those two types of unlabeled data that have been augmented, so it's the same image but it's been augmented different ways, you get similar predictions. So there's what's called a consistency loss. Obviously, in addition to the cross entropy that you use for labeled data as well. And so the limitation here is that, again, the augmentations are all in image space, and specifically kind of normal image processing augmentations that people have thought would be useful or effective. And so Mixup does a little bit of interesting thing where it does this interpolation, but it's still a very limited form of data augmentation. So what we actually want to do is data augmentation in feature space itself to perform really complex types of data augmentation. And so we've developed a method called FeatMatch, which uses a graph-based consistency method. And this is in submission. It'll come out pretty soon in archive. The key idea is that we want to construct a graph neural network in feature space to perform feature augmentation. So while on the lower left, you see the existing consistency-based methods that use very simple image-based augmentation. On the lower right, you see we'll actually build a graph. And this graph will consist of nodes, which are images, and edges, which are similarities between those images. And again, that's in feature space, not in pixel space, obviously. And since we can't really build a graph across all images in the entire data set, we actually abstract categories using what's called prototypes. So we just apply like k-means clustering to extract prototypes. And then given an image, an inference image, we build a graph between that image, again, in feature space, and the prototypes, which are, again, features. And so the output of this graph operation is refined features. So rather than each node being kind of the features being just the node level features, which are just extracted directly from the image itself, it actually refines the features to also incorporate the local neighborhood. So it kind of refines based on the features of the neighbors and kind of does a attention-based kind of combination. And that outputs a new set of features. What's interesting is in our work is that we look at this as data augmentation, because it's kind of augmenting or kind of manipulating the features based on this manifold neighborhood information. And so we actually apply this consistency loss. So that's the key to our method. You can see it on the bottom. We apply a consistency loss between the features before the graph and features after the graph. Again, kind of viewing this in the spirit of the graph being performing data augmentation, and then we perform some consistency to the non-augmented data and the augmented data. So I won't go into too much detail, but the graph module, again, is constructed between image features and a set of prototypes. Performing k-means, so we do this every epoch, is going to be cumbersome, computationally heavy if we extract all the features at all times, right, every epoch. And so what we actually use is kind of this momentum kind of approach. Actually, concurrently, there's some similar momentum ideas in self-supervised learning. But what we do is essentially, throughout the iterations, we extract features, and so we'll just store those features as we extract them throughout the iterations. And then at the end of the epoch, then we apply k-means to all the extracted features across the previous epoch. So there's some staleness there in the features that we're extracting because the parameters have been updated through the iterations, obviously, but it turns out not to matter. And so we just take all those features extracted throughout the iterations, apply k-means to them every epoch, which is pretty fast. And then those are our new prototypes that we apply to the graph. And so again, this is showing, I won't go too much detail, but this is showing kind of how every epoch we update the prototypes, and then we build new graphs between the instance, or the examples in the mini batch and those prototypes. And then we perform some graph-based augmentation and then apply this consistency loss. So to kind of differentiate our method from all the other ones, we're kind of one of the first methods that apply both image-based and feature-based augmentations. I mean, we still do, you know, again, the normal simple image-based augmentations, not complex ones like random augment. And the key though is that we do feature-based augmentation as well, that actually somehow leverages the structure of the feature space to do this more successfully. And it's kind of a learned augmentation because we're kind of updating the graph neural network parameters for the similarity function to perform better and better augmentation. So again, just tables showing on lots of data sets. So this is showing CIFAR 10, which is an SVHN, which is pretty small. But what's cool is that we can get pretty small amount of degradation when you go from, for SVHN, from 250 to 4,000 labeled examples, you only get something about 1% or less than 1% of the difference, which is kind of cool. And for larger data sets like CIFAR 100, mini ImageNet, again, we get some significant gains over the existing state of the art at the time. So I forgot to mention, we also, I mean, our method is orthogonal to what consistency-based method you also use. So we use mix match in this case. We can also, that's just because of the timing of the paper submission, but we can also use fixed match as well, or anything else that comes after that. One of the interesting things is that we've also done this on DomainNet. So DomainNet has 6 different domains. We use 5 of them here. And it has, I think, 345 classes. And so what we do is we provide out-of-distribution types of unlabeled data. So in semi-supervised learning, the idea is that you have a large unlabeled set. And here we're progressively adding more and more out-of-domain data. So in the form of covariate shift or domain shift in the unlabeled set. So this RU is really measuring how much of the labeled data we're replacing, or sorry, the unlabeled in-distribution data we're replacing with unlabeled out-of-distribution data. So for 0%, that means it's all in-distribution data. So that's kind of like our performance of if we have no out-of-distribution unlabeled data. And so again, we beat kind of the state of the art. And as we increase the amount of unlabeled out-of-distribution data all the way to 74%, which means that we replace 75% of the in-distribution unlabeled data with out-of-distribution unlabeled data, we do get a degradation. So these are error rates, but the degradation is not as much as state of the art. So this is by no means a solved problem, and I'll talk about that in a bit. So qualitative results, we can see that our data augmentation is actually kind of filling in the space more than image-based augmentation. So image-based augmentation, you see these kind of clusters or groupings when you consider the non-augmented and augmented data, whereas our case kind of augments across, kind of more uniformly across the feature space, which is really interesting because again, it's a more complex form of augmentation, and it's kind of a learned adaptive form of data augmentation. We can actually see kind of the what we actually have in terms of the variability in the prototypes themselves, and the similarity function that's learned within the graph neural network. We could see that the graph neural network has this kind of block diagonal structure, meaning that it's mostly leveraging in-class information. On the bottom, we can see that the selected prototypes have a pretty large kind of variability, which is what you would hope for in prototypes. One of the cool things that we can do is we can take the feature, which is the graph-based data augmentation, and what that graph outputs in terms of features, and find the closest image to it. And what we can show is this aug-F, which is our feature-based augmentation, actually takes the bird image, let's say a normal bird image on the ground that's zoomed in, and can actually perform feature augmentation to like flying birds. And so it's actually performing very complex augmentations. Of course, these are actually just pulled from real images because we can't really, we don't have a general model here that takes features into images, but we can actually see that at least in feature space, the augmentation corresponds to very complex different types of transformations that are still preserving the semantics, and we have losses that make sure that the augmented features, can still be used to classify the corresponding classes. So they will kind of still be semantic preserving as well. That's kind of, again, kind of work that we've done in terms of complex data augmentation. And so I think, with our work as well as lots of great work by others, I think, in domain semi-supervised and self-supervised learning is really starting to kind of, do really well and saturate. And so we want to kind of start moving beyond this, right? In the real world, we have large collections of unlabeled and labeled data from many different distributions, right? In domain and out of domain. And so there's different types of shift that can occur across these different things. So for example, there can be covariate shift, meaning that just the normal domain shift, meaning, for example, you have an image of a dog versus a sketch of a dog. You can also have semantic shift, right? Completely new classes. So can we leverage unlabeled data with completely new classes to improve semi-supervised learning, for example, which is, again, not a well understood problem. And so really kind of long term, I'm really interested in tackling methods that are combinations of multiple real world problems at once, not just one, right? Not just semi-supervised in domain, but actually semi-supervised combined with self-supervised combined with domain adaptation. So we have some early work, again, that's in submission that we're gonna release on arXiv pretty soon. That tries to use DomainNet to do this. So DomainNet is a really cool data set. I really like that work. It's really kind of awesome resource for researchers. It has 6 domains and a large kind of amount of data. So it has 345 classes, which is really cool. And then over kind of 600K training examples. And on the bottom, you see there's different kind of super classes or super categories that you can group the actual classes within, which is, again, also a useful thing to have. And so what we're going to do is we developed a setting based on DomainNet to be able to systematically study cross-domain semi-supervised learning. So we have a common in-distribution set. So either, for example, animals or devices. So we do both of those separately. And 3 types of shifts. And what we do is we take the in-distribution labeled and unlabeled data and kind of continuously expand the unlabeled data with more and more out-of-distribution unlabeled examples. And we have a parameter M that actually modulates. So because you're kind of modulating the amount of shift as well as through the amount of unlabeled data that has this shift. So as M increases, the number of unlabeled examples with out-of-distribution or domain shift, both covariate shift or semantic shift, can kind of, that increases, and so that increases the total amount of shift that you have in the unlabeled set. So what's cool is, again, the setting kind of decomposes these different things. We can study, how much shift there is, and we can study kind of the 3 different types of shift: covariate shift, semantic shift, and both of them together in a systematic way. So this is showing some examples. So On the lower left, you see the in-distribution data. So these are just real images of dogs or animals in general, actually. On the upper left, you see kind of covariate shift. So this can be sketches or other art, but again, of animals. On the lower right, you see semantic shift, meaning it's completely new classes, but it's still real images. And then upper right, you see both of these types of together. So these are no longer real images, and they're also no longer animals, for example. And so we can, again, look at the amount of shift and the type of shift and see how that affects semi-supervised learning. And so this is some preliminary result. There's going to be a lot more in our archive submission, conference submission. But in general, we do see a significant degradation as you add more out-of-distribution data. So on the x-axis here, M, or the amount of out-of-distribution data, increases. And what we see on the y-axis, which is the accuracy, is that you do get a very significant type of shift. Here we show both CS, which is covariate shift, SS, which is semantic shift, and MS is mixed shift. And what's interesting is that we show that this OOD data is not actually the problem. So if we remove it from the actual batches, that we remove the out-of-distribution data from the mini batches, then it still actually doesn't perform well. So this is that B-OOD case. And what you see is still pretty low compared to having actual OOD data within the mini batches with covariate shift and semantic shift. So FeatMatch, which is the kind of method that we're using here, kind of degrades, and not because it can't use the out-of-distribution data, but because of other kind of batch effects and things like that that we analyze in the paper. So sorry, there's missing text there, but the conclusion here is really that this type of out-of-distribution data in unlabeled, in the unlabeled case for semi-supervised learning, is still kind of an unsolved problem, and one that we've developed a setting that where you can systematically study this and try to improve the methods. So in conclusion, there's been amazing gains that have been made across learning with limited data. So data augmentation has been a crucial thing. I've showed two methods that we've developed that tries to not hand code the type of augmentation. So we use Stylization to develop data augmentation that tries to leverage the implicit variability within the data sources in domain generalization case. And then for semi-supervised learning, we've shown we can use graph neural networks, leveraging the structure of the manifold to perform data augmentation, complex feature space data augmentation to improve results. And again, we're kind of starting to move beyond these in-domain settings to be able to systematically study out-of-distribution data in the unlabeled semi-supervised learning case. And the long-term kind of goal is to, again, combine many of these different settings together, because that's both practically useful and also kind of scientifically interesting. So in summary, I'd like to acknowledge all my PhD students. So they do all the hard work. So none of this would be possible without them. And then on the right, you see the various funding sources from DARPA, NSF, and industry. And with that, I hope it'll be an interesting discussion. And I'll